There were a lot of questions near the start about sunspots and their size, their shape, their duration. So many. So we had S. McNeil saying, "Are we in a sunspot minimum at the moment? What determines the duration of the sunspot cycle?" Asks Naomi. What's the connection between sunspot density and solar activity? Any of those you want to give a go to?
Yeah, absolutely. So I mean, sunspots are so fundamental, and we've only known about them for we've only known what they are since 1908. So for hundreds of years, thousands of years, we've known the sun has these black spots on the sun. They can be many times the size of the Earth, and they can live from anything from, I don't know, a couple of days up to many weeks. And their size dictates their lifetime. So the bigger they are, the longer they live for. Now, the key bit of information that actually I didn't really stress and I should have done is that sunspots are patches on the surface of the sun where there is a particularly strong magnetic field. And so in my mind, I visualize the magnetic field as being like a tree trunk that kind of comes from the interior of the sun through the surface and into the atmosphere, where it branches out to form these lovely arches. So that intersection of a strong magnetic field with the photosphere is where the sunspot forms, and it forms because the magnetic field in that region allows the gas there to cool down, so it doesn't glow as brightly as the surrounding gas. So if you see a sunspot on the sun, you can think, that's a region of strong magnetic field. And with specialist telescopes, we can look at them and we can detect the magnetic fields. I didn't show any of those images, but we have that ability. So typically I would look at the sunspots in a telescope that is able to directly measure the magnetic field and know what's the field strength, what's the polarity, is it a north pole or a south pole? And so sunspots are regions of strong magnetic field. So as that solar cycle goes up and down, it's actually because the sun's magnetism is changing and kind of pulsing in strength and complexity. So at sunspot minimum, where we are now, there are a few sunspots because the magnetic field of the sun is not as strong and it's in a much more simple state. When we go up to solar maximum, we get sunspots on the surface. They represent lots of bar magnets on the surface of the sun. So you've got an overall dipolar field of the sun, and then the sunspots are all these magnetic regions on the surface too. So sunspots and magnetisms and the solar cycle are all tied together. We don't know why the solar cycle is 11 years. That's the solar cycle is a big focus of the solar orbiter mission. And what we're trying to do is understand how the flows of fluid, of plasma in the sun, evolve the magnetic field. This comes back to this tying together of magnetism and plasma. So you can evolve and move the magnetic field through these plasma flows.
So does that mean that coronal mass ejections are more likely when there's more sunspots and a sort of sunspot maximum? Yes.
Yeah, absolutely. So coronal mass ejections are a magnetic phenomenon, and they are produced from these sunspot regions. Yeah, they are sort of expulsions of magnetic field from the sunspot regions.
Yeah. We've got a whole load of questions on coronal mass ejections, as you'd imagine. One person, Lawrence, asks: are CMEs basically unidirectional, like everywhere, all across the sun, or are they more common at the equator or the poles? Or
yeah, that's a good question. So they are more common. We don't really see them at the poles, but their spread reflects where the sunspots form on the sun. Maybe that's the way to think about it. And sunspots at the start of the solar cycle form at about plus and minus 30 degrees from the equator. And as the cycle progresses, the sunspots appear closer and closer to the equator. Now, there's a lot more in it than that, but you could sort of conceptualize that coronal mass ejections pretty much form within, I don't know, a few tens of degrees north of the equator and a few tens of degrees south, with a few maybe higher latitudes.
So once they're ejected, how do we track them? Do we look at their, I don't know, through a telescope, or how can we track them?
Yeah, so we can use these artificial solar eclipse telescopes. You can use telescopes, that produce artificial solar eclipses, and then you see the coronal mass ejection ejected as a white cloud that moves away from the sun. So hopefully with Lagrange, we'll see those white clouds leave the sun and travel to the Earth, and hopefully we'll be able to track them for a decent amount of the way. And we did have a sort of like a precursor mission almost. The stereo mission from NASA has a telescope on board that allows us to do that. And so we know it's possible. We know we can build the instruments, we know we can process the data, and we know we can track them. Or we can use other sources like radio data, because the moving electrons in these structures give off radio data. So you can track them partly through their journey from that.
And how long would it take for one to reach the Earth? Sorry, I think I missed that.
Yes, that's what I forgot to say. That's totally what I forgot to say.
Well, thanks to Stephen Roderick for that question.
Yeah, thank you. My whole slide about the Sun-Earth chain was to talk about the timescales, and I completely forgot to talk about the timescales there. So a coronal mass ejection will take anywhere between, say, 18 hours and 4 days to get to the Earth. So they have a range of speeds. The light from a solar flare takes 8 minutes. So you see this flash, because coronal mass ejections and flares can happen together. So quite often we'll see a flash of light, which is the solar flare. We're like, okay, what's happening in that region? And then later you can see in the artificial eclipse data the coronal mass ejection coming our way. Yeah.
There was a few questions here also about the magnetic reconnection, because I noticed, and I think other people noticed from your diagram, that the magnetic field on the sun was going this way, and the magnetic field on the Earth was going this way. Now, number one, does that mean the south pole of the sun is at the top compared to the Earth?
Yeah, so it's the sun's dipolar field flips every 11 years with the solar cycle.
Okay.
Another really interesting part of our star. So the Earth's magnetic field evolves on a much slower time scale. The sun is chung, chung, chung every 11 years, flipping. But then what comes from the sun in these coronal mass ejections can have any orientation. It depends on what formed at the sun, what that was like, and how it turned or rotated as it propagates to the Earth. So, as we were hoping with the study with Erika Palmerio at the University of Helsinki, we were hoping to see that some preservation of the magnetic field orientation at the sun in these erupting structures to be preserved when it got to the Earth, and that's not the case. They evolve.
Interesting.
Yeah.
So, there was another question here, which was about other times of sort of very significant magnetic field activity. Does that affect wildlife? Like, for example, Owen Donnelly asked, was there a noted impact on birds which use magnetic fields to help them migrate? Did they all end in the wrong place?
Yeah, I've read a lot about, well, not a lot. I've read some articles about that. So there is a growing, I think, awareness, especially among space scientists. I mean, there's a whole sort of animal navigation community that has been working on this for a long time. So I think, yes, the answer is yes. There are certain animals that navigate using the Earth's magnetic field. And when a strong space weather event happens and, it distorts the Earth's magnetic field, it moves their map. So then they're following a map that's now not taking them in the right direction. And there's been cases of like racing pigeons getting lost. I think there was a study about whales recently getting lost too. So I think there's a pretty strong feeling that yes, animals navigate by magnetic fields and they get impacted by space weather. Then there's the kind of more detailed analysis around what is it within them and where are the magnetic receptors that allow them to navigate by magnetic fields. And I think there was some work at UCL by Mark Lithgow who was trying to find where is it in a bird's head that they have the magnetic receptors. I can't remember what happened with that.
Well, presumably it all messes up when you put it in an NMR machine anyway, so I'm not sure how you would find that out.
Yeah, I don't know how he was doing the study. Yeah, you could. You could be quite cruel, couldn't you? Yeah.
Just while we're on the subject of the magnetic field still, Amog Rakesh asks a question which I was actually thinking. So obviously in the Earth, if I dimly remember my GCSE geology, we have this molten iron core that creates a magnetic field. But what is it in the sun that's creating that magnetic field?
Yeah, so the sun has part of that question I can answer, and part I have to defer to other astrophysicists, because I mentioned that the sun formed from a vast cloud of gas and dust that collapsed down, and at the centre of that collapsed cloud then the sun formed, and that initial cloud is thought to have had its own magnetic field. So that's a question that goes back, oh gosh, what is the origin of cosmic magnetic fields after the Big Bang? So that's a question for astrophysicists that I don't know the answer to that. So as far as we understand it, there was this primordial magnetic field. That's pretty certain. We see magnetic fields all throughout the universe. So there was a magnetic field in this cloud, and as the cloud collapsed down, the magnetic field went with it. So the sun had a sort of seed magnetic field when it was formed 4,500 million years ago. And then that seed magnetic field has been amplified and evolved by these fluid flows in the sun. So if people want to look it up, it's called the solar dynamo, and you'll find out the details of the processes that evolve this seed magnetic field. And over the solar cycle, the seed field becomes stronger. Well, the overall field of the sun rather becomes stronger and weaker as this dynamo process goes on.
We had quite a few, just to finish, we had quite a few questions about the sort of damage and impact that some of these things might have. So Paul Harrison asks, have any studies been done on the 11-year cycle of the sun, correlating that with instances of skin cancer? Is that?
I'm not sure about that. Yeah, about that aspect, because I mean, the variation over the 11-year cycle, there's a strong magnetic field variation which influences solar flares, coronal mass ejections, how big they are, how fast they are, how frequent they are. There's also a change in the sun's radiated output, which is not by very much, but it depends on what wavelength of light you consider. So there's a fairly big variation in wavelengths like X-rays and extreme ultraviolet light, but overall, adding it up, it's a fraction of a percent. But not all of that light makes it through the Earth's atmosphere. So we've got this protective shield. So I suspect that probably any risks like that are taken away because the variations overall are very small, and the Earth's atmosphere is absorbing a lot of that radiation as well. Yeah. And actually, while I think about it, it's on a completely different note, but you mentioned Chris Brockley-Blatt earlier is answering questions. So Chris Brockley-Blatt is one of the engineers who worked on the Solar Orbiter mission and made the mission happen. So you're getting answers from an expert. So I'm really grateful that Chris has joined us and is able to answer the questions. Thanks.
Oh, that's fantastic. And actually, on that protective shield angle, Oscar Rowe asked, what threats would space weather pose to inhabiting planets such as Mars? I would have thought quite a lot would be my amateur's guess.
Yeah, yes. And so, and that's another area that's looked at. So Erica Palmero, whose work I talked about, she's now looking at space weather on Mars. So she's moved from, looking at the sun sort of to the Earth and now onto Mars. And Mars doesn't have much of a magnetic field or atmosphere to speak about. And that's why you would be vulnerable on the surface of Mars, particularly to high energy particles. So I didn't talk about them too much, but when a coronal mass ejection is launched, it kind of, it expands out into the solar system, and it acts a bit like a snowplow. And if it's moving fast enough, the coronal mass ejection will generate a shock at its leading edge. And in that shock, it will accelerate particles that get to the Earth in maybe half an hour or so. Very high energy particles traveling, decent amount of the speed of light. Those high energy particles, for us, we have a protective shield to some of them, depending on their energy. On Mars, you don't have that. So those particles can just reach you down to the surface of the planet. And I think it's that lack of shielding that means for humans going there, you would have to make your own shield. So some material, I've heard people thinking about, water. So the water that you're using could also be used as a shield against the radiation, some sort of clever, innovative ways, because taking shielding is mass and launching mass is expensive. But if you want to minimize that particle radiation, which could lead to leukemias or cell damage, that's absolutely key. And all these long-term studies on the space station, sort of the preliminary studies to help the scientists understand what those risks really are. But when you're on your way to Mars or you're on Mars, you've got to take your own shielding.
So just to finish, this isn't a great question to finish on, but it's a question I actually want to know the answer to. And Eric Reinecke asked it right at the start, and Leah, you asked it right at the end. So, which is this idea of, is the sun a typical star? Are there any other kinds of stars out there in the galaxy that have different, CMEs and sunspots, and is the sun fairly average or below average?
Really depends on what characteristics you're looking at. So it's, in some senses, most stars are smaller and cooler than our sun. So you might think, oh, it's kind of stand out in its size. But actually, if we think about activity levels, the Kepler mission, which looked at many, many other sun-like stars, found that they can be much more active than our sun. So their flares and presumably also coronal mass ejections can be thousands of times more energetic than the ones we see on our local star. So there's also a sort of line of thinking that, okay, our sun is not average in some senses because it's quite massive relative to most other stars, but maybe it's not that active compared to other sun-like stars. And that is probably good for us. That's the case.
Well, thank you, Lucie. I did say that was the last question. There was one more question from Naomi Dubois. She asks, is the cushion behind Professor Green meant to look like the sun? Would you like to tell people about your cushion before we finish?
Yes. So this was made for me by Katie Steckles, who's a mathematician, maths communicator, and it's one of my favourite gifts. So it is the sun, and it's even got, I don't know how I put it the right way, magnetic arches. I don't know if you can see that. Magnetic arches in its atmosphere, and sunspots. So white patches are sort of north poles and black patches are the south pole. So it's got sunspots and arches and kind of nice fluffy surface. So yeah, that's my sun.